Welcome to section 3. In this section, we will have a look at what is inside the trochlear model. Now, let's have a look at the flow of this model, from the input image to the final text output. The model recognizes text from an input image by following these steps. First, we go from image to patches, in the sense that the input image is divided into smaller, fixed-size patches, which are flattened into vectors. Second, these vectors are converted into high-dimensional vectors called patch embeddings, with added position embeddings to retain spatial information. Then we have the encoder, which processes these embeddings through multiple layers of multi-head attention and feed-forward networks, refining the representation of the image patches. And finally, we have the decoder, which converts the encoded representations into a sequence of text. More specifically, it processes the shifted output sequence through masked multi-head attention, and feed-forward layers to produce the final text output sequence. So the final result is a sequence of tokens representing the text extracted from the input image, such as, in this case, licensee of McDonald's. Introduced by Vaswani et al. In 2017, transformers are particularly noted for their high parallelizability, which facilitates efficient training on a large scale. This efficiency, in turn, has encouraged the development of modern accelerators like GPUs and TPUs, which are tuned for transformers, thus creating a prime example of the so-called hardware lottery. Transformers are used for a wide range of AI tasks, from natural language processing to vision and to robotics. They start by modeling the input as a set of tokens. In natural language processing, tokens can be parts of words. In vision, image patches. These tokens then interact in multiple stages through an attention mechanism. Finally, the output of the network can be read in a variety of ways to perform classification, regression, or autoregressive generation. To recap, transformers model inputs as a set of tokens that interact with each other in multiple stages through an attention mechanism. This approach enables the model to capture intricate patterns and relationships in the data, making it very effective for various tasks, like language translation, text generation, and image recognition. Let's now walk through the various components of a single encoder layer, as illustrated in the diagram. At the bottom, we start with the input vectors x1 and x2, which represent the token embeddings of the input sequence. These embeddings are enhanced by adding positional encodings to incorporate the order of the tokens. The positional encoding helps the model understand the position of each token in the sequence, which is crucial since the transformer architecture itself does not have any inherent notion of word order. The first major block within the encoder is the self-attention mechanism. Here, the input embeddings, x1 and x2, are processed to generate new representations, z1 and z2. Self-attention allows each token to focus on different parts of the input sequence, capturing dependencies irrespective of their distance from each other in the sequence. The outputs z1 and z2 from the self-attention mechanism are then passed to an add and normalize layer. In this layer, the original input embeddings x1 and x2 are added to their corresponding self-attention outputs z1 and z2, respectively. This is followed by layer normalization. And the purpose of adding the original input is to provide a residual connection, which helps in training deeper networks by mitigating the vanishing gradient problem. The normalized outputs are then passed through a feed-forward neural network. This network is the same for each position and consists of two linear transformations with a ReLU activation in between. Each of these transformations is applied independently to each position, hence the term feed-forward. And similar to the previous step, the output from the feed-forward network is again combined with its input through an add and normalize layer, providing another residual connection and normalization step. The final output Z1 and Z2, after these operations, are the new representations of the tokens, which now carry both contextual information and positional encoding. These outputs can then be passed to the next encoder layer, if multiple layers are used, or to the subsequent stages in the transformer model. To summarize, Each encoder layer in the transformer model consists of two main sublayers, the self-attention mechanism and the feed-forward network. Each sublayer is followed by an add and normalize operation, and this architecture allows the model to capture complex dependencies in the input sequence and transform the token embeddings into richer representations. Let's now talk about the inductive biases in transformers. Transformers display permutation equivariance, meaning that the model's output does not change if the order of the input data is altered. This may seem surprising because transformers are often used for modeling sequences like sentences where order matters. Sensitivity to position is recovered by using position encoding, which tags each token with its position in a sequence or grid. Moreover, central to the transformer architecture is the attention mechanism. This feature allows the model to selectively concentrate on different parts of the input data. This capability is critical for the model's overall performance, and this is a topic that we will delve deeper into on day 4. High-capacity transformers have a remarkable ability to learn inductive biases from data exposure and augmentations, enhancing their generalization capabilities. In practice, achieving generalization often involves training on a broad spectrum of data. The extensive datasets available today enable models like transformers to be exposed to far more data than single humans or animals in their lifetimes.